So we're going to start off with topic 6.1, endothermic versus exothermic processes. Determine if each of the following are endothermic or exothermic. Restart when you are done. So for the first one, freezing is going from a liquid to a solid. So the particles are getting closer together, so they're forming IMFs, so that's going to be exo. Burning wood is exo because it's releasing heat. You can feel that heat when burning wood. The next one says that we had 5 grams of ammonium nitrate, we dissolved it in water, and the temperature went down. Because the temperature went down, it must be absorbing energy, so that would be endothermic. And finally, condensation is going from a gas to a liquid. So just like number 1, we're forming IMF, so that's going to be exo. Anytime we form intermolecular forces, it's going to release energy because breaking intermolecular forces requires energy and is endothermic. So boiling or vaporization would be going from a liquid to a gas, so that would be endothermic. When a salt dissolves, the heat of solution, or delta H, can be endothermic or exothermic. It depends on the inter- and intramolecular forces that are being broken and formed. While delta S, or the entropy of solution, generally increases as a salt dissolves, because we have a pure solid and a pure liquid, and then we mix the two, which generally results in more microstates or more entropy. Go ahead and pause the video and read this problem. Figure out which steps are endothermic and which steps are exothermic. Restart when you are done. So in step 1, we are separation between ions. Notice that the particles are spreading out, and if we're spreading the particles out, that's going to require energy, so that's going to be endothermic. In step 2, the polar solvent is expanded. So again, we're breaking intermolecular forces, or at least weakening them to get these gaps. So that's going to be endothermic. And then step 3, the particles are attracting and they're going together, so we're forming attractions. So that would be exothermic. So if you said D, steps 1 and 2 are endo and the last step is exo, you are correct. To figure out if the overall dissolution of a solid is endo or exo, it depends on what these actual values are. If this was positive 5 and this was positive 10 and this was negative 20, then the overall process would be exothermic. But if this was negative 15, positive 15, positive 10, and negative 20, the overall process would be endothermic. You also have to be able to read energy diagrams. For energy diagrams, exothermic processes lose energy. So the potential energy of the products are less than the reactants. So on this graph, it says which one is endothermic and which one is exothermic. So what we talked about a second ago, we have reactants and products. The difference in our reactants and products is our delta H. In A, we absorbed energy because the products have more energy than what we started with. And if we did products minus reactants, that would result in a positive delta H value. So this one is endothermic. While B, my products have less energy than where I started, so they must have released energy. And again, if I did products minus reactants, that would result in a negative delta H. So this one is exo. So the things you need to know about heat transfer is particles in a warmer body have a greater kinetic energy than those in a cooler body. When those particles collide, they're going to transfer thermal energy. That's heat transfer, heat exchange, or transfer of energy. Eventually, though, the thermal equilibrium is reached as the particles continue to collide. Particles always move or transfer energy from warmer bodies to cooler bodies until they're both at the same temperature, which again is thermal equilibrium. Temperature is a measure of the average kinetic energy of a substance, while heat is the total energy due to molecular motion in a substance and is measured in joules. So temperature is degrees Celsius and heat is going to be joules or kilojoules. Make sure you know that temperature is directly related to Kelvin temperature. Whoever has a higher Kelvin temperature has more kinetic energy. Make sure that you can read graphs like this, the Boltzmann distributions. You can see it in the sense of this problem where it says which graph or which curve, T1 or T2, represents a higher temperature. Or it can also be, when we talk about gases, which gas is diffusing at a greater rate. So T2 is the higher temp. Because it's got a larger range in kinetic energy. If we draw a line down from roughly the center of that curve, T2 has a higher kinetic energy than T1 does. We have to have the same area under the curve, so the higher temp, or the one that moves with more kinetic energy, is going to be further to the right and it's going to be further down. Notice it's kind of squattier. So it's kind of pushed down to spread the molecules out because we need more at this higher kinetic energy. Remember that this is an average kinetic energy, so some molecules are going to be moving faster, some molecules are going to be moving slower, but on average, the ones at a higher temp will be moving with more kinetic energy. So again, the peak of this curve should be more to the right and further down than the lower temp. Lower temp is always higher up and further to the left. So go ahead and pause the video and try this one, which relates that information that we just talked about. Restart when you're done. So B is wrong because the area under the curve is not the same in those two graphs. We want a lower temperature as the dashed curve. Well, if it's a lower temperature, they should be moving slower, so it should be more to the left, the peak. A would be at a higher temperature. C also is incorrect because if it's moving to the right, it should be also going down or becoming flatter or lower down. And then D, notice it moved to the left and it went further up. So D is our correct answer. The molecules are moving slower and there's less spread. You also may have to interpret a particle diagram representing velocities. To represent the velocities, you can draw an arrow. The shorter the arrow, the lower the speed. So this one would be slower and this one would be a faster molecule. So go ahead and pause the video and draw a picture of T1. So this one was T1 and a picture of T2. Go ahead and draw 5 atoms of each of the gases. Restart when you are done. So T1 should be at a lower temp, so I should have more of the shorter arrows. They're going to be going in different directions. And I may have even a longer one, but again, they're on average going to be shorter than the ones over here that are at a higher temperature. But just like that, I could have maybe a smaller arrow in T2. But again, on average, my T2 is faster, so it's going to have longer lines representing that they're moving faster. We said before that heat is going to be transferred from an object with a higher temperature to an object with a lower temperature when the particles collide with each other. Particles do not absorb or release the same amount of energy per gram. The amount of energy that they can transfer per gram is the specific heat or related to the specific heat. So you may need to calculate the Q or heat absorbed or released in a system undergoing heat or cooling given the heat capacity and change in temperature. We would do that using this equation, Q equals mc delta T. We may also have a calorimetry problem where the heat lost is equal to my heat gained. So one substance loses energy and the other substance gains energy. Negative Q equals positive Q. Down here it says that you may have specific heat capacity as well as molar heat capacity. If I had, let's say, water at 4.184 joules per gram degrees Celsius, I could convert that to molar heat capacity by changing my grams to moles. Well, if I was to do grams to moles, there's my grams, so I have to have it diagonal to cancel it out. And 1 mole is 18.02 grams for water. That would give me my molar heat capacity. So then my units would be joules per mole degrees Celsius. And degrees Celsius and Kelvin are going to be used interchangeably because the difference in temperature for Celsius or Kelvin is the same. So occasionally you'll see joules per mole times Kelvin. That would be the same as joules per gram degrees Celsius. So looking at it a little bit more, specific heat capacity, again, is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. An object with a large heat capacity can absorb a lot of heat without undergoing much change in temperature, because it would require more energy for it to go up a degree. While objects with small heat capacities have large increases and decreases in temperature, with only a small amount of heat being absorbed or released. So remember our Q equals mc delta T. Q is heat. It's going to be in joules or calories or maybe even kilojoules. Mass is going to be in grams, sometimes kilograms, but most time grams. C is Cp. So joules per gram degrees Celsius is our most common, but just make sure all of your units are canceling. Because if you had calories per gram degrees Celsius, you'd want to make sure that you used calories. Or if it was molar heat capacity, we would want to use moles as our mass. And then our delta T is going to be either in Kelvin or degrees Celsius. And the delta means change. So go ahead and pause the video and read this problem and figure out which substance would reach the highest temperature when the same amount of energy is applied to an equal mass sample. So if you said mercury, you are correct. Because mercury has the lowest specific heat capacity, it only requires 0.14 joules to raise it 1 gram by 1 degree Celsius, while aluminum would require 0.89 joules to raise that same amount 1 degree Celsius. So mercury would go up many more degrees Celsius than aluminum would go up just 1. So that same idea, go ahead and read this one and try it. Restart when you're done. So for this problem, we still had 1 gram, but in this case, we heated all of them to the same temperature and then dropped them into water. The substance that absorbs the most energy would release the most energy. So aluminum would require the most energy to reach 150 degrees Celsius. Therefore, it would release the most energy into water when it is placed into the water. Therefore, water would go up the most degrees with aluminum. Mercury would increase the temperature of the water the least because it would absorb the least amount of energy. The first law of thermodynamics says that energy of the universe is constant. Energy can be neither created nor destroyed. So while energy can be converted in a chemical process, the total energy remains constant. Energy can be transferred as heat or work. Our change in energy is equal to Q plus W. Q is heat, W is work. When Q is negative, it's exothermic. And if Q is positive, then it's endothermic. So releases energy, absorbs energy. When work is negative, that means that work is being done on the surroundings. And if work is positive, then it's work is being done on the system. So our change in energy, so delta E equals Q plus W. Our delta E is negative 5.155, and that's equal to our Q, and it says the system absorbs energy, so that's positive or endothermic. So that's 2,500 joules. And this one was kilojoules. Notice those aren't in the same unit. So I need to change this one to joules by multiplying by 1,000. So 2,500 plus X is equal to negative 5,155. So without a calculator, that means my answer must be 7.655. And it must be a negative answer. So if it's negative work, then my system is doing work on the surroundings because it's going out. So the system performs that much work on the surroundings. Had it been positive, then the system has that much work done by the surroundings. Calorimetry is our law of conservation of energy. Energy can't be lost or gained. So negative Q equals Q, or negative MC delta T equals MC delta T. My final temperature is going to be somewhere in the middle of my two temperatures. So we know we're using calorimetry because we have two different substances. The substance starting at the higher temperature is going to get the negative sign. In this case, that's iron, because iron's starting at 90 while water's starting at 15. So negative MC delta T is equal to MCP delta T. This is my iron and this is my water. My iron has a mass of 50. I'm looking for the iron CP. And my delta T is final minus initial. My final is always of both substances, even though it says it's just of water. That's the temperature I'm measuring is the water, but they have to be the same temp. And then my water is 30 mils, but I know that 1 gram equals 1 milliliter because that's the density of water. My CP of water should be given. So that's not something that you would need to know for the test. So 4.184 joules per gram degree Celsius, and sometimes they also just say 4.18. And then my change in temperature, 19.3 minus 15. Simplifying that down, I have a negative, and this is also going to be a negative, so those cancel out. Your negatives should be canceling out. And then simplifying all of this, so I subtract and then multiply. And then divide by my 3535. So 0.153 joules per gram degree Celsius. Go ahead and pause the video and try this error analysis question on your own. Restart when you've got your answer. So in this calorimetry experiment, where the student messed up is they failed to put the top on the cup. Therefore, some of the heat was able to escape. So my heat lost should equal my heat gained. But I didn't gain all the energy that was lost. Therefore, this number is going to be too small. So if I had 5x is equal to 10, well then my CP or x would equal 2. But in reality, maybe instead of 10, maybe it was 15. So then my x should have equaled 3. So notice that the calculated value, which is this one, is too small because this is the true value. And I just made up those calculated and true values. You could calculate it out. The CP would be about 1.5 difference. But without actually solving it out, because you wouldn't have a calculator in the multiple choice section, you could make up some numbers and be like, okay, well, if this lost energy and this gained, but I didn't gain all the energy, this number is smaller, therefore my specific heat would be smaller as well. So the correct answer is B, the calculated value would be too small because of the heat lost to the surroundings. So in this section, we're talking about the energy of phase changes. So energy has to be transferred for a system to cause a substance to melt or boil, and the energy absorbed during a phase change is equal to the energy released during a complementary phase change. So solid to liquid is melting, liquid to solid is freezing. Any of the ones that are getting spread out are going to be endothermic. So this one's endo, and this one is endo. While their complementary changes are going to be exothermic because they're the reverse. So as the particles are getting closer together, they're going to be exothermic and releasing, and as we pull them apart, endothermic. Heat of fusion is the energy that must be put into a solid to melt it. Or, in the reverse of that, it'll be the energy that's released when a substance freezes. Heat of vaporization is the energy that must be put into a liquid to turn it into a gas. And again, the energy that would be released when a substance condensates. Here's a phase diagram. So as we go up the graph, it's endo, and as we go down the graph, all of these are exothermic. Notice that when a substance undergoes a phase change, it's in equilibrium and the temperature is constant. So it's being held constant there, and it's being held constant here. In the first section, we have all solid. So in this section, it's a pure solid that's being heated. In this section, it's a pure liquid being heated. And in the last section, it's a pure gas being heated. When a substance is changing temperatures, we're going to use Q equals MC delta T. So that's going to be on all the slopes. And then on these straightaways, when temperature is no longer changing, that's when we're going to use Q equals MC delta whatever it is. So on this first one, it would be Q equals MHF, and on the second one, Q equals MHV. Notice there's no degree sign change or no delta T because temperature is not changing in a phase change. So here's a problem that was on a past AP problem, or on a past AP exam. Go ahead and pause the video and try A. So figure out how much energy is needed to recycle aluminum by melting it. So for part A, we need to heat the solid up and then we need to melt the solid. So we're going to do 2 steps. The first step, I need to heat the solid up, so I'm using MC delta T. I don't know my Q, but my mass was 1 mole. The CP of aluminum is 24 joules per mole times Kelvin. Notice that my moles cancel out, so I don't need to convert this to grams. And my delta T, it started at 298 and now it's at 933. So 933 minus 298. Solving that out, I get that many joules. So then on part B, or the second part, when I'm melting it, I'm going to use Q equals MHF. So my Q, I don't know. My mass is still 1 mole. And my HF is 10.7 kilojoules per mole. If I had forgotten that conversion or forgot my equation, I could just look at the units of HF and realize I just needed to multiply by my moles so that my units would cancel out. Doing so gives me 10.7 kilojoules. My last step is I need to add step A and B up, but if you notice, those are not in the same unit. So make sure that you're paying attention to units. So I can divide this by 1,000 joules to give me my 15.2 kilojoules. So 15.2 plus 10.7 is 25.9 kilojoules. So that's my answer to A. So now go ahead and read B and see how much energy it would take to extract aluminum from that same amount and see which one is greater, the recycling or extracting. So for part B, I have the same amount of aluminum because if I don't have the same amount of aluminum, then I can't compare. They said for every 2 moles of aluminum, this is how much energy is going to be needed. Notice it's positive, so that's endothermic. So for every 2 moles of aluminum, I have 1675 kilojoules. So that's 838 kilojoules. These two have to be in the same unit, so had I converted A to joules, I couldn't have compared them. I have to have them both in kilojoules and shown as kilojoules on my paper, or again, I cannot make a comparison. 838 kilojoules is greater than 25.9 kilojoules. So we want to know which one requires less energy. So recycling requires less energy. So that was my full answer. Go ahead and pause the video and read through this problem, seeing which answer is the best. Restart when you're done. So this one's a little bit more with calorimetry than phase changes, but we have 50 grams and 50 grams. So the temperature is the same. We can see that the metal changed quite a bit. It changed about 59 degrees, while the water went down by about 21 degrees. So why did the water change a lot more than the metal, even though they had the same mass? So if you said C, you are correct. So the metal temperature changed more than the water temperature did, but the amount of thermal energy gained or lost is the same to the amount of thermal energy lost by the water. So the heat lost had to equal the heat gained. They had differing amounts of delta T because water has a higher specific heat than the metal. Therefore, it required more energy for the water to go up a degree than the metal to go down a degree. So enthalpy is delta H, and we can calculate the amount of heat absorbed or released by a system when given the amount of a substance reacting in either moles or given the molar enthalpy of reaction. So what that means, here we have a balanced equation and we have a delta H. What is the change in enthalpy or the change in delta H when 46 grams of NH3 react with excess N2O? So we're not calculating the delta H per mole because this is always per mole, regardless of if it tells you it's per mole of reaction. What that means is for every 2 moles of NH3, it'll produce 10 kilojoules. or for every 3 moles of N2O, it'll produce this amount of energy. When it produces 4 moles of N2, the same amount of energy, or 3 moles of water, it'll produce the same amount of energy. So we want to know how much energy will be produced or absorbed when this grams of NH3 react. So step 1 is I need to convert my NH3 to moles. This is basically a stoichiometry problem where step 1 is you convert to moles. My molar mass from the periodic table is 17.034. Once I have my moles, I can do a mole to energy ratio instead of a mole to mole ratio. So I need to get rid of my moles of NH3, and I'm converting to kilojoules. I know that there's 2 moles of NH3 for every negative 1010 kilojoules. My units cancel out, leaving me with kilojoules. And so I get negative 1363.7, or in 3 sig figs, negative 1360 kilojoules. I need the negative in front because this problem says what's the change in enthalpy. If it had said how much energy would be released, then I could have just said 1360 kilojoules released at the end. But delta H's should have signs on them, and so that's why you needed that negative. So there are multiple ways of calculating delta H, or enthalpy. We can do delta H of formations, we can do bond energy, we can do Hess's law. Let's look at bond energy first. So bond energy is the energy required to break a bond. Because the breaking of a bond is always an endothermic process, because bonds don't just break apart, bond energy is always a positive number. When a bond is formed, energy equal to the bond energy is released. If the overall delta H is positive, then the reactants have more energy. So delta H is equal to bonds broken minus bonds formed. My bonds broken are reactants, and my bonds formed are products. So again, if delta H is positive, and this value is positive, and this value is positive, because delta H, or my bond energy, is always positive, a positive minus a positive means that the reactants have more energy. If my delta H is negative, well, a positive minus a positive means that my products have more energy. You may also see a bond energy graph like this. On here, left to right is distance, so we can see that in this graphic more easily. So bond length is left to right, and bond energy, or the strength of the bond, is up and down. So the stronger the bond, the further down it's going to be. If you have a double or triple bond, then the bond length is going to be a little bit shorter. Or if the 2 atoms can get closer together, they're going to be further to the left. Bond length is the perfect medium between the atoms being too close, because if they're too close, they're going to repel, and being too far apart. If they're too far apart, then there's going to be no attractions. So the atoms have to be optimally separated where energy is at a minimum. This is the amount of energy. It's negative, so that's how much energy would be released when this bond forms. Therefore, I would have to put that much energy into it to break the bond. Bond energy, or the strength of a bond, is related to 3 things: the size, HCl versus HBr. Well, Br is bigger than Cl, so we would think that HBr's bond would be easier to break. So bigger is generally weaker because it would make the bond length longer. Longer bond lengths are going to be weaker. Polarity, HCl versus HH. Well, the HCl is more polar. The more polar it is, the electrons are pulled to one side of the atom versus the other, weakening that bond. That's why HF, even though HF is very polar, so you'd expect it to break apart, fluorine is very small, and so that's why HF is a weak acid compared to HCl and HBr and HI. And then bond order. Bond order has to do with the number of bonds between two atoms. So this one has a bond order of 3, bond order of 2, and bond order of 1. If we look on this picture, this one has a bond strength of 941. So the bond energy is 941 kilojoules needed to break it. This one is 418, and this one is 391. So the bigger the bond order, the stronger the bond is if it's between equal atoms. So triple is always stronger than a single bond. We can also calculate bond energy by using that equation I had mentioned earlier. Delta H is equal to the bond energies of bonds broken minus the sum of the bond energies of bonds formed. Broken is your reactants, and formed is your products. It's the only equation in our thermo units that's reactants minus products. All other times it's products minus reactants. Sometimes it helps if you draw the molecules out. So in this case I have HH, but I have two HHs. So I can either put a 2 in front like that, or I can draw the molecules out twice so I can see that I have to break 2 HH bonds. I have an OO and I have 2 waters. So again, I can draw it twice, or I'm going to put parentheses around this one. I'm going to do my reactants first. So my delta H is equal to 2 HHs, so 436, plus 1 OO double bond at 499, minus, I've got 2 bonds of OH, but I have a 2 in front, so 2 times 2, 4 OH bonds. So all together on this one, I get my delta H is equal to negative 481 kilojoules per mole. So it says, do the reactants or products have more energy? Well, since my delta H is negative, my products have more energy. I can also see that in this calculation. If I break down the problem to my reactants and products, my reactants had 1371 kilojoules, and my products have 1852 needed. So my products have a larger bond energy. Go ahead and pause the video and try this one on your own. You're trying to figure out which one represents H2, O2, and N2. So those are our 3 substances. So figure out which one corresponds to X, which one corresponds to Y, and which one corresponds to Z. The first one that I would look at is the one that's the furthest down. That means that it's the strongest bond. HH is a single bond, OO is a double bond, and nitrogen is a triple bond. Well, a triple bond is going to be the strongest bond, so I know that Y2, which is this one, corresponds to the triple bond. Just knowing that, I know the answer is A. But I could also look at X2 and Y2, or Z2. Z2 is a little bit further down. Not a whole lot, but it's a little bit further down. And it's more to the right, meaning it's bigger. So Z2 must be a stronger bond, and it must be a little bit bigger than X2. Which makes sense because X2 is a single bond, but its atoms are very, very tiny, so they can get really close together. And they're going to be relatively strong because they can get so close together. While O2 with that double bond is going to take up more space and be further to the right because it takes up more space, and a little bit further down because it has that double bond. So enthalpy of formation is using our equation products minus reactants, and we're using HF values. So enthalpy or heat of formation is the change in energy that takes place when 1 mole of a compound is formed from its component pure elements under standard state conditions. Because of that definition, HF for pure elements is always 0. So if you have just pure sodium, that's going to be 0. Or if you had any of the diatomics as gases, they're going to be 0. If the value for delta HF is negative, energy was released when the compound is formed, and the product is therefore more stable than the elements that made it up. So go ahead and pause the video and try this one on your own. Remember that it, like most of the equations in the thermo sections, are going to be products minus reactants. So remember that we wanted to do products and then reactants. You do need to multiply by coefficients, so 2 times my CO2, which was negative 394, plus 4 times negative 242. That's all my products minus my reactants, so 2 times negative 201. And I could say plus 3 at 0, or I could just leave that off since it is a 0. For a problem like this, I would recommend breaking it up and finding my total products. My total products is 1756. All of that minus my reactants, which are negative 402. Therefore, my delta H is negative 1354 kilojoules per mole. So this reaction is exothermic because delta H is negative. Finally, the last one is Hess's law. So Hess's law is saying that we can add up the delta H's for reactions to get the overall delta H of a new reaction. When doing delta H's, if you flip the equation, then we're going to flip the sign on the enthalpy value. If we multiply or divide an equation, then we're going to also multiply or divide the enthalpy value by that same number. For delta H problems, remember that it always comes back to the equation that we don't know the delta H for. So I would look for NH3 first. NH3 is located here, and it's only in this second equation. So then I ask myself, is it in the right location? No. I need it as a reactant, and it's currently a product. So I know I'm going to have to flip this equation. Then I say, well, is it at the right number? No, I have 4, or I have 2, and I need 4. So I'm also going to have to times it by 2. So I do highly recommend rewriting the equation when you flip it or multiply it, and make sure that you're paying attention to what the delta H is now. So if I flip it, it turns positive, and if I times it by 2, I get 183.6 kilojoules per mole. And then I'm going to draw a line through that one so I don't accidentally add it up later. I like to circle the compounds when I get them in the right spot, so I know that I can no longer touch that equation, or I'm going to mess up what's currently in the correct spot. Next, I have oxygen, but oxygen's in more than one equation. It's in the first and third equation. So I'm going to leave that alone for now. So I'm going to find my NO. NO is only in this first equation. It's in the right location, but it's not the correct number. I need 4 as a product. I only have 2 as a product, so I'm going to have to times this reaction by 2. So again, I'm going to rewrite, and when I rewrite, I'm also trying to be neat. And I need to multiply my delta H by 2. So 180.6 times 2. So now my NO is in the right spot. And so the last one I need to get is my my waters. So water is in this last equation. It is in the right spot, but it's not the correct number, so I'm going to have to multiply this one by 3. So now I have 6H2 plus 3O2. And my delta H, I need to multiply it by 3, giving me negative 1451.1. So now I need to fix my oxygens. Well, I've circled something in every equation now, so hopefully they work out. I need 5 as a reactant. Well, I've got 2 and I've got 3. They're both on the left side of the arrow. If they're on the same side of the arrow, they're going to add up. So 2 plus 3 gives me 5, so those are good. Anything on opposite sides of the arrow are going to cancel out. So 2 and 2 nitrogens, 6 and 6. Make sure you're crossing out things that are not in your overall equation, because sometimes you have an equation that's given only to make sure everything crosses out. My last step is to add up all my delta H's. And I got negative 906.3 kilojoules per mole. So again, this reaction is exothermic.